last talks, so I'm happy that some people still survived until the end of this week. So I will talk about joint work with Untitled, and it's about some corrections to mesoscopic correlations in random band matrices. And I will present some, maybe come here because you will see it better. So I will present some rigorous results that will be the solid part of the talk, but I will present also some kind of speculations which relate this material to physics, to various physics results, and there I'm a bit more on a more shaky ground, so maybe there will be some people, especially in the physics audience, physics community, who will protest some of the statements which I'm making. I will try to make them in a less controversial form, but the mathematical part will be solid. Okay, so let me just go through a few of the basic transparencies at the beginning. These are well known to this audience. So of course, we have this well-known universality. Disaster. It worked.
Yeah, I'm trying to get that the mute button off the screen.
Oh. Okay. Good. Okay. So, so of course, this universality picture is well known for general disordered quantum systems in this audience. So there are two types of behaviors. Either you have the localized situation, localized regime, which can be characterized by various features. It's in terms of eigenvectors, lack of transport, or Poisson local statistics. And this is in contrast to the other regime, the delocalized regime, random matrix statistics, and so on. This didn't disappear, but anyway. Now, of course, I mean, at very first sight, the localization is the surprising regime, and that was the original invention of Anderson. If you think about a very naive way, then you just do a little perturbation to the free Laplacian, then you would expect that it remains delocalized. Nevertheless, it's true. On the other hand, mathematically, the localized regime is much more accessible, and basically we have strong results in that direction, but in the delocalized regime, we have much less results. Okay. So there is this dichotomy, and of course, there are various models when one can study this dichotomy. It's supposed to be a general dichotomy for disordered systems. So the two popular models is the random Schrödinger operators. Maybe I don't have to introduce it here. So this is just an electron hopping on say on a lattice with random potentials. If you think about a matrix representation of that, then it looks like a tri-diagonal matrix, at least in one dimension. And in that situation, you have the behavior, the first type of behavior, the localization of the Poisson statistics. Now, the other regime, other well-studied model is the opposite, the completely mean field regime, which is the Wigner random matrices, and that, of course, again, needs no introduction here. Here I'm talking about really the Wigner situation, so not the invariant models. So I think of the H, X, Y, these are random transition probabilities, the random variables, expectation 0, and they have some variance structure. Now, here every site is connected with every site. There is no spatial structure in the system. So in particular, the dimension is irrelevant. There is no dimension, or dimension is 0 if you wish. Now, this one is it follows the second, the localized behavior, random matrix statistics, and so on. And I will talk about an intermediate model, which was also discussed in this conference, especially yesterday by Sherbina's talk. These are the random band matrices which interpolate between these two models, and therefore they are good playground. They can be used for testing various things. They can be used to test the transition between these two regimes. That's one possible use. The other possible use, and that's what we are focused on today, is testing the quantum diffusion, trying to prove or see how much quantum diffusion one can rigorously prove. Now here is a little bit more precise with the definition. It's exactly the same thing what Sherbina introduced yesterday. So I imagine that the matrix elements are labeled by elements in a big box. The box has linear size L. It's in d dimensions, so the total volume number of sites is L to the d. Expectation is 0. I'm talking about the hermitian case. We will do both symmetric class. Actually, the results change a little bit, but one can do both cases. And the important thing is that the entries are independent. and they are independent, but they are not identically distributed, especially they have a non-trivial variance profile, which I will write in this form. So I will use this f as a profile function. The f is a probability distribution, even function, non-negative function on Rd, and then this f on a scale w creates the variance structure. The important parameter in the model is the w, that's called the bandwidth. This tells you which sites are connected at least in one step, how far one quantum jump goes. So f, you think of f being some localized function, with some fuzz decay. So if x and y are bigger than w, then this is small. Okay, so that's the basic setup. And now, of course, because the variance structure is non-trivial, it introduces a space structure. Now it does matter what is your base space, what is the space which you use to label the matrix elements. So it has some spatial structure, but on the other hand, so like the random Schrödinger, but on the other hand, technically it's a much more accessible model than the random Schrödinger. The random Schrödinger is somehow too brutal. This one is still closer to the mean field situation. You can do many more things in that. And of course, there have been many papers on the physics literature. I didn't try to write up all the names who worked on the physics side. Unfortunately, Fyodorov is not here anymore, but I think he was one of the first one who promoted from the physics side. And then there have been much fewer, but still several mathematical results, mathematical rigorous results on this model, and they were reviewed yesterday, more details by Sherbina, so let me not put it here anymore. Just for a normalization, I'm using the standard normalization, namely that the semicircle, so this one has a density of states, which is given by the semicircle law. Semicircle law is normalized to be -2, 2. So in particular, the level density, the level spacing is of order 1 over L to the D. L to the D is like the N, the capital N, typically the size of the matrix. And the delta is the level spacing, so it's essentially 1 over the number of sides. Good. Now, the quantity which we are interested in, actually it's a quantity which you can ask in general disordered system, not just for random band matrices, is the standard linear statistics. So lambdas are the eigenvalues, and I'm asking for the energy density, the eigenvalue density around a fixed energy E on a certain scale. Eta, these will be important parameters in the model, so maybe let me just roughly keep these scales here. So the total spectrum is between -2 and 2. We always talk about a fixed energy E. The E is always in the bulk. I'm not talking about edge behavior. Then you have eigenvalues. The typical distance between eigenvalues is this 1 over L to the D, which is like 1 over N. And then we look at a certain regime. We take some cutoff function. We take some profile function, which has a scale eta. So this is the typical picture you should think about. We can, of course, study, depending how this scale eta relates to the delta. Delta is this level spacing. You talk about different regimes. So the most important regime is, which has been also discussed basically in this conference in full details, is the microscopic scale. That's the regime where eta is of order delta. You are down on the scale of the level spacing, and then of course the big question is whether it's Poisson or random matrix statistics. Yes.
So the W has disappeared. Is it not yet important?
It's not yet important. Now, as I said, this is in general disordered system. It will certainly come. But this kind of question you can ask in full generality. Of course, you are right that my picture sort of indicates that this is the random matrix. So that's why actually I'm using this. I'm using a little bit the physics notation. So this delta is the standard notation in physics for level spacing. And this you can also ask for random Schrödinger. This is the smallest energy scale. And since we are testing the eigenvalues on a scale eta, it's natural to ask look at various regimes, and if eta is on the scale of the level spacing, then you detect, then such a quantity, such linear statistics detects individual eigenvalues. So that's called the microscopic scale. Then there is the macroscopic scale when eta is large, eta is order 1, and then there is no universality and it's model dependent. I mean, of course, if it's a Wigner random matrix, then you have the semicircle O, but if you take some random Schrödinger or you take some more general matrix model, then the macroscopic profile will depend on that model. So these are the two well-studied regimes, and today's talk is about the mesoscopic scale, when this eta is sort of much smaller than the global spectrum, but it's bigger than the eigenvalue spacing, so it detects many eigenvalues, but not all eigenvalues at the same time. Exactly in the same way as the talk just before my talk explained that. Okay, and in this regime there will be universalities with certain phase transitions. I would like to explain this a little bit better. Now, there is a special physical motivation to study mesoscopic scale. At least this is one which I'm aware of. Maybe there are many others. And this goes back to Tauler's theory about fluctuation of conductance. You can study how this ordered metallic sample, the conductance fluctuates. And part of this fluctuation comes from the fluctuation of the number of states, or the density around the Fermi level on a microscopic, on a mesoscopic window. So that's one reason why you want to understand that. But of course, it's also a mathematically interesting thing because it also exhibits certain universality. So let me just do a very back of the envelope calculation. So you are interested in this. Maybe I should write up this y. So this y is the basic quantity. It has various parameters. It's a function. It's a function eta. This is this function eta, function phi on a scale eta, and then you ask for the number of eigenvalues. You ask for the eigenvalue, some of the eigenvalue statistics around the energy E. So this is the basic quantity what I'm going to look at. And the natural question is that you look at the statistics of several of these objects. So you can also change the energy. You can take these mesoscopic windows at different energies, and in principle, I didn't put it here, you can also change the profile function. No, I think it in the phi of eta there is an eta. Yes. Okay. Good. So now let me just look at the 2-point correlation function. That's of course the most important thing. And now so this is an exact identity. P2 is the truncated correlation function of the eigenvalues. And now so now you want to compute this thing, but this is now integrated on a larger scale. So if you plug it in, for example, if you ask the same question about the GUE, so if the sign kernel statistics applies, then in this formula you can put in the sign kernel, and after some little calculation you end up integrating the sign kernel, but integrating a sign kernel on a larger scale, on a scale. So I put it in, the integration variable is eta. You integrate around the shift. So you put two different energies, energy and E minus omega and E plus omega. So you take the correlation of two different energies. And then you look at the situation when this omega, which is the distance between two energies. So maybe let me draw the picture which corresponds there. So there is an E. There is an E minus omega over 2, E plus omega over 2, and you look at this test function which lives on the scale eta. And in that particular question, I'm looking at the situation when the omega is bigger than the eta. So I take two energies which are far away from each other. Far away in a sense that they are farther away than the mesoscopic scale. But of course, the scale is still mesoscopic, so the eta is still much bigger than the eigenvalue spacing. So I detect many eigenvalues, and the window is far away. So this is this situation here. And now if you do this, if you look at this situation, you assume that the sign kernel holds, the sign kernel statistics holds also in this mesoscopic scale, and you do the calculation, then what you see is, of course, you have to do an integration, but this integration is on the scale of eta. Essentially, or actually it's even a larger scale, so a scale of omega. So the short scale fluctuation on the sign kernel disappears. What survives here is only the global profile, the global envelope of the sign kernel, which boils down to 1 over omega squared decay. So the bottom line is that the correlation between these two quantities, these two densities, decays like the distance between the two energies squared. That's what the sign kernel predicts. Now, of course, this is a fishy thing, because this is if the sign kernel holds. And one has to be careful, because the sign kernel, of course, is established for GUE, but it's established for the microscopic statistics. It's not really established for the macroscopic or mesoscopic scales. Although, so this looks easy in this way, and it's tempting to assume that it's true in every scale. And actually, as far as this calculation is concerned for the GUE, this relation was indeed proved rigorously more than 10 years ago by Buteler-Monver and Korunji for the GUE case, and then there were some results for the Wigner case as well. So if you ask this type of question, you can strictly for the GUE, then you can still use the sign kernel, although there are various caveats to that. So here are the caveats in more general situations. So first of all, you don't expect this to hold for general delocalized systems. So unlike the local statistics, microscopic statistics is supposed to follow the sign kernel basically no matter what kind of delocalized system you have, as long as the symmetry class is correct. This relation here, when you try to use it for the mesoscopic statistics, it's not true in general on mesoscopic scales, and I will come to that more precisely what is true. It has been known in the physics literature a long time ago, and these are given by the so-called Altshuler-Shklovsky formulas, and there's a phase transition here up to a certain level it's true, and below that it's not true. And actually, this is one of our rigorous results, that we prove these Altshuler-Shklovsky formulas, at least for random band matrices. This is one thing, one warning sign. The other warning sign is that the sign kernel might be correct, and in certain cases it is correct up to the leading term, but it fails to predict the subleading terms. And this is our other rigorous result. And actually, this result is a new observation which seems to contradict various physics predictions, and I will come to that. Yeah?
Can I just check? I think what's the situation for the CUE? I think there it's much simpler, right?
Probably we didn't look at CUE. We didn't.
One has a formula there for any scale.
Yes.
Yeah, exactly.
Then sign kernel works.
Not trivial to GUE. No.
Okay, so we didn't look at CUE. Maybe we should do that. Okay, so now let me explain to you this Altshuler-Shklovsky formulas, and especially the phase transition. And there is a phase transition which is called a tau-less, which happens at the so-called tau-less energy, and this is the following quantity. So first of all, in this system, you have a disordered system with a space structure, and in such a system, you expect quantum diffusion. Now, in certain situations, it has been proven with more or less rigor. For the random band matrices, the model which we look at, actually, we did it in an earlier work with Dante. We precisely proved the quantum diffusion. We figured out the diffusion coefficient. And the tau-less energy, which is the basic scale, the threshold in this model, is related to the diffusion coefficient. I call it eta 0. It will be a spectral scale, but the way to think about it is really an inverse of the time, and inverse of the time for the quantum diffusion to reach the boundary. I mean, we are in a finite system, linear size lambda, linear size L, and then you ask yourself that if you start from the roughly somewhere in the middle of the system, how, and if you assume that the quantum, true quantum evolution, unitary evolution evolves by quantum diffusion approximation is correct, then you ask yourself how much time it takes to reach the boundary, and this, of course, depends on the diffusion coefficient divided by R squared. So everything boils down to a diffusion coefficient, which for random matrices, we rigorously prove that it's of order W squared, so now W appears in the game. Now, here are these Archer-Shklovsky formulas, and the behavior depends on whether this eta, the scale, the mesoscopic scale, where you ask the question, whether this mesoscopic scale is bigger or smaller than this eta 0, this very specific parameter. And there are two regimes. Either you are in the diffusion regime. Diffusion regime is a large eta. Now eta is like inverse to the conjugate variable of the time. So large eta means small time or smaller time. So the eta bigger than eta 0 is the regime where the time is not long enough to reach the boundary. That's where you see non-trivial diffusion profile emerging. The other regime where eta is smaller than eta 0, that's the regime where the quantum diffusion already equilibrated. So then you don't see space structure anymore. And the formulas are the following. So I just wrote up two formulas. There are many more. I wrote up the formula for the variance of one of these y's, one of the y, and I wrote up also a two-point correlation function in a situation where two energies are different. So the first statement is about the variance of that quantity, the second statement about the correlation, truncated correlation of that quantity. And here is there is the relation. I mean, there are all kinds of constants in front of that also, which I didn't put in. But the important thing is that there is a definite, let me talk about a second one. So there is a definite exponent here, and this exponent depends on dimension. It's d over 2 minus 2. So depending on the dimension, as long as you are in diffusion regime, the correlation decay between these two statistics, how it's power law in the difference in the omega variable, but the power depends on the dimension. And this is true in 1 and 3 dimensions. I will come back in a moment what happens in a 2-dimensional case. And then similarly there is a relation, there is a statement about the variance. Now this is the diffusion regime. Now the other regime, the mean field regime, where the eta is small, so eta is, when small eta means that the time is large, then exactly the same formulas hold, but d equals 0. Plug in d equals 0 here. So d equals 0 is the 0-dimensional case, which is the mean field regime, and nothing, and there is no space structure. Now, I mean, these formulas can be used for various things. One thing which one can use for, and one can look at it, it's an amusing thing. You can compare it with the Poisson statistics. You can ask yourself, I mean, here I'm talking about decay of correlations. You can compare this regime, the random matrix regime, with the presumed localization regime. There you can ask the same kind of question: what is the correlation between these two statistics if they were really Poisson? Now there is also a caveat here, because if the eigenvalues were strictly, if the points were strictly Poisson and these are separated, then there is no correlation. But on the other hand, one has to be careful, because the Poisson statistics in the localized regime does not claim that it's Poisson on every scale. It claims on the local scale again. You don't expect that the global or even mesoscopic statistics, even if in localized regime, you don't expect that it will be the eigenvalues here and the eigenvalues here will be completely independent. That you don't expect. And actually, actually you can use this to predict the Anderson transition. In the following way, because you can go back. So I mean, you have the variance in the Archer-Shklovsky tells you the variance in the diffusion regime, and also you know that if it were Poisson, you know how it should behave, and the variance is proportional with the number. I mean, the eta times y is the number of eigenvalues in the interval. Y was the density. So the variance of the number proportional with the number characterizes the Poisson distribution, and this you can use to predict the Anderson transition in the way, I don't want to go into the details, it's an old argument, but you have to remember why you expect Poisson statistics for the localized regime. And you expect Poisson statistics because you expect there's a localization length, and you expect that the parameters are set up in such a way that the eigenfunctions do not overlap. So, and then you have to do a little counting, because as long as you just take a few eigenvalues, so you take a very, very local statistics, then of course then you just consider a few eigenvectors, and the few eigenvectors are really independently distributed in the space. But if the statistics, if the eta gets larger and larger, then you start monitoring more and more eigenvectors, and sooner or later they will start overlapping even if they are localized. So if you put all these arguments together, then you get an estimate then you get a prediction on the localization length, and this result is actually it coincides with the predicted Anderson transition in the band matrices, which were discussed yesterday as well. So in this random band matrices in one dimension, we expect that the localization length is W squared. And that's exactly, after doing this translation, that's exactly the crossover regime, the transition regime, when this variance and this variance are equal. Okay, so this is one remark. This has been known a long time ago. Now, the other remark which I would like to make is that you may say that what happens in 2 dimensions, apparently there is no, the theorem doesn't cover 2 dimensions, and there is a good reason for it. It does cover, but in 2 dimensions, the 2 dimension is the critical situation for various reasons. Especially in the 2-dimensional case, the leading term vanishes, and then you can ask about the subleading terms. So this we will do, but I think we will do on the next slide. Yeah.
3 dimensions, we go back to
Yeah, I will have a more precise theorem about 2 dimensions. Yes, but this is a typical situation, and that's what characterizes criticality, that something vanishes. And
Yeah, I don't see it vanishing up this whole that
What?
happens.
no, this one doesn't vanish, but there is a coefficient in front of that, and that vanishes. I will state the theorem. I think maybe there will be a theorem more precisely. So this is actually the mathematical theorem. So we are doing everything in I state everything in a diffusion regime. We have results in the other regime as well, but for simplicity, let me do that. So this is a diffusive regime. That's the natural condition. And technically, we have to assume that eta is not too small. Ideally, one would like to go down to that scale, but there's another technical lower bound on eta, which is the w to the minus d third. We are always away from the spectral edges, and we are looking for the spectral correlator, so we just normalize the truncated correlation function. We do it because that's typical in physics literature. That's the quantity one looks at. And the result is the following. There is a prefactor, which is a fairly small prefactor. This already indicates that the question what we are looking at is non-trivial. It's a much smaller quantity than the y's themselves. And then the result is that, so it's a limiting statement, of course. The result is this correlation is given by a function theta, which has an explicit formula, and I will come back to that. I will show these formulas in certain regimes, plus some error term. And this formula depends only on the band profile f. Remember, f was the profile describing the variance of the band matrix, but otherwise it's independent of the distribution of the matrix elements. So depends only on the variance. So that's type of universality, you wish. The first type of universality. Now, as I said, a technical bound is needed. Actually, if I want to be absolutely precise, this technical bound is needed if you have a specific profile, which is the characteristic function profile. And if you take a general f, then this bound, this lower restriction is even more stringent. We need more larger lower bound on eta. Now, what is theta? For physicists, the theta is the one-loop diagrams after self-energy renormalization. It's a number which you can represent in diagrammatic calculation. I will show it more precisely a little bit by formulas, but I just say this is absolutely explicit. It's a little bit ugly expression, but it's explicit, it's computable. And this I already mentioned that actually the leading term is already a higher order effect. So because there is a here I'm computing the truncated correlation. So there's a huge cancellation already here. So that's why the problem is technically not so easy, because you have to compute, you have to trace all kinds of cancellations, even to be able to state, to get the right order of that object. Now here is this leading diagram, and I'm not going to introduce you Feynman diagrams in full generality here, especially not in the last talk of the conference and before lunch, but just the diagrammatic picture. So first of all, you do the self-energy renormalization, which is sort of summing up the single tadpole diagram. So these are the two-legged subdiagrams where you sum up all of them. If you haven't seen that before, you will not understand this line, but there is a resummation procedure for the propagator. You do it up to all order. That's the first thing what you do. And then the second, so then the blue line will refer to this renormalized propagator. And then here is the leading term. The leading term is the so-called one-loop diagram. Now, what this is? So you are computing, you are basically computing the correlation function of two traces. I mean, y is roughly speaking like the number of eigenvalues, like the density of states in a certain interval. So this can be expressed by the trace of the imaginary part of the Green's function. So if we have two of them, you have two of them. Good. Now each of these traces can be represented by one of these particle lines, and it's a closed line because it's got the trace, and then there's another trace outside. So this is roughly what this picture represents. And then when you take the expectation, then you have lots of connections. I mean, this comes from when you do some expansion, and when you take expectation, then you start computing variances of the matrix elements, and then certain connections are represented by these graphs. Okay, so there's a nice graphical expression for some ugly explicit formulas. So this is the graph which gives you the leading term. That's actually the first graph what you can imagine. This is a connected graph. Connected means that the two particle lines are connected because you take the truncated correlation function. And apart from that, this is sort of the simplest one what you do. It consists of ladder diagrams. These are sort of this so-called specific structure when you take the expectation value. And then the formula is given here, very roughly speaking, after you summed up these ladder diagrams. These ladder diagrams sum up by a geometric series, and it's given by a formula like that. Here S is the variance profile. It's a matrix, and is given by a trace of a certain expression of this matrix, where the energy difference, the E1 and D2, appears explicitly down in the denominator. Okay, so now if you believe that this is the only diagram which contributes, then you can do a fairly easy calculation, which I don't want to go through in details, but basically you just say that this S is given by the profile function f, and then it's translation invariant. So you go to Fourier transform, you start seeing the diffusion, the second moment of the profile appearing. You do a little bit calculation, and you pull out the relevant parameter, which is the E1 minus E2, and it comes out with this magic exponent d over 2 minus 2 times various explicit scaling factors in front of that, times a number. It's an explicit number which is given by an integrand. This is this integral what it gives you. It's a specific function integrated over Rd. I call this Kd. It can be computed, and this number happens to be 0 when d equals 2. So that's the feature of the special special case of 2D in 2 dimensions. Then the naive calculation, well, even it's not so naive, but the calculation of this leading one-loop diagram gives you 0, not because the exponent is wrong, but because the prefactor is 0. Okay. You can also ask the question in 4 dimensions. Then we also have a result. Then you get logarithmic divergence, and also you see from this little calculation that 4 is the critical dimension for this problem. If d is bigger or equal than 5, then the main contribution to this integral comes from not from the small q regime, but from the large q regime, or the medial or the intermediate q regime. And then it starts depending not just the first order, second order Taylor expansion of f hat around 0, but it starts depending on the whole profile, and then you get a non-universal behavior. Non-universal in a sense that the answer still depends only on the variance profile, but it's not a simple power law, it's something else. Good. Now what happens in 2 dimensions? Well, 2 dimensions the leading term vanishes, but then you can just do this calculation a little bit further. You can expand it up to 4th order, you do again the calculation, and you get a logarithmic correction. And also it starts depending on not just the second moment, but on the 4th moment. So you have this x, and we prove it rigorously that the next order correction is really this logarithmic. Now, and this is the first our first controversy because this result seems to contradict to another prediction, which was done by Kravtsov and Lerner, who predicted in the 2-dimensional case, it's called a weak localization correction, who predicted this kind of behavior. There's a difference whether it's beta equal 1 or beta equal 2, but it's completely different than ours. I mean, ours is logarithmic. The prefactor is always the same. But theirs is power law in omega times some fairly small prefactor. So actually our rigorously proven result is much bigger than the prediction here. And the important thing is that the W, negative power of W in front. And moreover, that's why it's especially interesting that that the prediction here arises from a somewhat different argument. They arise from a so-called 2-loop diagram, which is also called a figure 8 diagram or Hikami boxes, depending on which community you come from. And it's this kind of diagram. So again, you have the 2 particle lines, but then you try to you sort of form this figure 8 picture, as it's shown on the picture, and then here you can put extra connections in this red box. It's called the Hikami box. And you can do 3 different things. Either you don't put any connection, or you put this connection when you connect both of these connections are intra-particle lines. You connect the outer with the outer, or you connect the intern with the inter. And then the claim in these people who do this game, especially Kravtsov and Lerner, they claim that the sum of these 3 diagrams, each of them is fairly big, but they cancel each other. So that's why the final result is much smaller than each of the diagrams would predict. That's the cancellation. So that's the main claim. There's a cancellation among these diagrams. And our rigorous result is that actually there is no such cancellation, at least in our model, at least in the random band models. Our contribution comes actually from the first diagram, and the other 2 diagrams are proved to be smaller. There is no such cancellation, which is behind this Hikami box. Okay, so that's one of the results, one of the controversial results. The other one is the following: you can ask the same question for Wigner matrices. There is no space dependence now, so it's very easy. You again ask the question about the density-density correlator. That's again the same thing what we had in the previous talk. Here I use a little bit different notation because again, for physicists, they recognize the formulas better if I use a different notation. So here I introduce this S, which is the L times omega. So now I'm doing everything within 1 dimension. So S is a parameter which measures the distance between the 2 energies, but in units of level spacing. So S is a big number. That's what they prefer to use. So here I rewrote the same quantity. In that way, everything is measured in terms of delta, which is the level spacing. So this is the function Rs, the correlator function. But very often they look at its Fourier transform, which is typically denoted by K. This is called a form factor. And now here you start seeing the difference in the statistics. So the Wigner-Dyson statistics, if Wigner-Dyson holds, if it held, then the following is true. In beta equal 2, you just have 1 over s square. This is the same thing as the 1 over omega square, but now with a different scaling. This is in beta equal 2, and beta equal 1, it's 1 plus nothing. In beta equal 1, it's 1 plus there is a correction term, which is this 1 over s. And this comes from the Hikami term. If you try to predict this thing, if you try to compute what these people do, you try to compute these things for the Wigner matrix by diagrammatic perturbation theory, then you face with the same Hikami type diagrams, and this gives you that number or that term. Or in many papers, if you look at them, many papers they compute this form factor, and then it looks like that it's linear. It starts linearly. This is a small tau regime. It starts linearly, that corresponds to this leading term, and then the subleading term is this quadratic correction.
So can I just check
Yeah.
what you said? Is R not a real function?
R is a real function here.
So what's this one over
Yes,
five?
okay, yeah, that's right, sorry. Yeah, that's also a physics convention which actually took us some time to understand. So because this y, you're completely right. These formulas are for the situation when the phi is the 1 over lambda minus I eta. So you take the resolvent. These are actually for the resolvent. Yes. Good. So this is the prediction if the Wigner-Dyson statistics held on every scale or the scale on which we look at, and this is our result. This is again a rigorous result. So here you look at the regime where the omega, the spacing is the distance between these two things is again bigger than eta, but the eta is larger than L to the minus 1/2. So let me be precise. So now I'm doing the Wigner case. So the level spacing is 1 over L, and eta being L to the minus 1/2 is sort of halfway between 1 and the smallest scale. So if L is bigger, if eta is large, this is a large mesoscopic scale, then we have a following expansion that's rigorous for this function Rs. There is the one which you expect. Then there are blue terms. These are not that important. The blue terms, these are well understood. They come from various corrections, explicit corrections from this one loop diagram calculation. I showed you that there is a formula in the one loop diagram, and when you compute it, there are corrections there. That's not so interesting. But the interesting thing is this term, which is L over S square, and this is a term which comes from this first Hikami box, which is the uncancelled term in the Hikami box, and this term should be compared with the predicted term, which comes from the Hikami box if the Hikami box cancellation were valid. But at least what we prove is that at least in this regime, in our regime, this Hikami box is not cancelled, and we get a term which is much bigger than what the physicists predict in this situation. Now, of course, it's very hard to read physics papers in this business, especially because you see these formulas disappear at least 10 at least I've seen it in 10 different papers, and they all show very precisely when there are further corrections, further terms there. But typically they don't say in which regime they expect this to hold. You know, there are various. This is supposed to hold on the large S regime, but there's an underlying L, the macroscopic size of the system, and which one goes first to infinity before the other, that's usually left quite vague. So we are not questioning that these formulas may be correct when S is not too big. What we say that when this S is big, it's L to the 1/2, then it's not correct. Actually, our expansion, as I say, so our expansion is valid only, and we have results only in the situation when this S is bigger than L 1/2. Yes. Well, they never. Yes. Okay, I will come to that. Hopefully, they will do vanish. Yes. Okay. So now here is some philosophy about that, but again, I may be attacked for that. So here are the two different situations. This is what the Wigner-Dyson predicts. I removed these blue terms, which are not the important one. The important one is this Hikami term, and this is what we actually prove in the regime where S is big. Now, I know at least 3 different folklore physics arguments for this thing. At least 3 different methods. Maybe people know further methods. One of them is this diagrammatic resolvent perturbation theory. Just look at the Wigner matrices, blindly expand and then do various resummations. This is, for example, how the Kravtsov-Lerner paper did it. There's another method which goes under the name of semi-classical periodic orbit theory, and there's a huge machinery. Many people make a living out of it. And this is an idea where they think in the following way that this is not just for random matrices, it's for any disordered quantum system. They say that the quantum state in the semi-classical regime, they set up in model in such a way that in the semi-classical regime, then the quantum state should be supported around the periodic trajectory. So it's some kind of WKB state which lives around the periodic trajectory. And then they ask you, then they see that the correlation between eigenvalues, this corresponds to interferences, quantum interferences between wave functions sitting along various periodic trajectories. It's a completely different picture. And if you look at that, if you look at those papers, then in those papers, they also, you see pictures like that, which correspond to our leading one-loop diagram. But this picture is supposed to be, it's not in an abstract space, it's in the configuration space, and it's supposed to be a wave function. This is a periodic trajectory, and there is supposed to be a wave function sitting concentrated on that trajectory, and this gives the leading term. And then in these papers, you also see these figure 8 diagrams, and also you see all kinds of avoided crossings of the figure 8 diagrams. And these are, so the picture is the same, the diagrams are the same, but they mean completely different things because they are still, they mean periodic orbits in the actual physical space. And then you ask yourself how many times it happens that a periodic orbit, the same periodic orbit, gets close to itself, and moreover gets close to itself in such a way that the angle of incidence is small, so that there is a long time. Let's draw it a little bit longer, so that there is a long spatial regime where the two phases may interfere, and from this phase interference they deduce the sub-leading term. And it's a figure 8 diagram. It gives it's responsible for the same term, namely for that term here, but the meaning of the diagram is completely different. And then there is a third third model, which is a sigma model calculation. This is what I'm least familiar with, but this also predicts this thing. Now, here's the surprising thing, that the first two models are from mathematical point of view, first two methods, from mathematical point of view, are completely crazy. These are potentially unstable in the regime where the S is small. S is this L times omega. So the S is related to level spacing. The smaller level spacing means that the time is longer. So in other words, you have to do an expansion, either a diagrammatic expansion or the semi-classical periodic expansion, taking into account very, very long trajectories, for example, in semi-classical expansion, or taking into account exponentially many diagrams. And what they claim is that out of these exponentially many diagrams or periodic orbits, nothing else matters, just these two. This is the leading term, and this is the sub-leading term, and there are exponentially many others which they neglect. And this sounds crazier and crazier as you take more and more of them. And that's exactly a regime where S is small. But nevertheless, this calculation reproduces the Wigner-Dyson statistics, and reproduces it even better, reproduces better and better as S gets small. So it's a somewhat crazy situation that you do an expansion which is completely unjustified, even more and more unjustified if S is small, but it gives you a better and better result. And therefore, there was no doubt about the applicability of this, at least I haven't read it anywhere, there was no doubt about the applicability of these ideas, neither the diagrammatic expansion and semi-classical periodic orbit theory, in the mesoscopic regime. Because it holds in the smallest scale, gives like the Wigner-Dyson, and the neglected terms are just less and less dangerous if S gets bigger and bigger. So it was sort of assumed, I guess it was assumed that it's true on every mesoscopic scale, but it's not. It's on once this S is larger than this L to the 1/2, then it's not true. Okay, so that's what I'm saying here. in the 1 and 2. Now the number 3 is a different object. The number 3, the sigma model calculation, as much as I understand, this is something which tends to be more exact for small s, for the small scale. So there is a complementary situation here. For the small scale, the sigma model is supposed to be correct. For larger, for large s, the diagrammatic perturbations here, the way how we do it rigorously, that seems to be correct. Okay, so actually we don't have a result yet about the sigma model calculation, but there's a work in progress with Alex Hartland. We have to team up with some physicists to understand what they do. But it seems to be that he sees in his calculations, he sees that this L to the 1/2 is really a threshold for breaking down. So what we are claiming that if S is large, then our expansion is correct, and what hopefully he will claim in his calculation that if S is small, but smaller than L to the 1/2, then the sigma model calculation is still reliable, but it breaks down once it reaches the L to the 1/2. So this L to the 1/2 is supposed to be a threshold above which our method, our standard diagrammatic perturbation is correct, and below that, hopefully the sigma model calculation is correct. Okay, so I mean, here is just the culprit, the reason for this diagram. I don't want to go through in details. We use the same diagram. It's always the same diagram. It's a figure 8 diagram. But of course, what the diagram precisely means, that comes from the context. And in our case, this diagram, the way how we do the calculation, what our diagram means, there is a power counting behind that, which counts the number of ladders. Each of the ladder diagram has a certain contribution. Then it counts how many labels you can assign to various points. Let me not go through it. It's before lunch. So this is the way how we compute, and then this gives our contribution. Now we have further results as well. Just I flash it up quickly. So of course I just talked about the 2-point correlation function, but actually we can do it any point correlation function. It's asymptotic Gaussian. That's not the joint statistics of that. It's not a surprising thing. We can also do criticality. I already talked about the critical phenomena in D equal 2 dimension. That's for the short-range decay, short-range variance decay. There's another critical model which is called a critical band matrix. This we have seen in Fyodorov's talk. That's a one-dimensional model, but the variance decay is slow. It's quadratic. And that behaves exactly in the same way as the two-dimensional model, two-dimensional short-scale decaying model, in a way that the leading term vanishes and we compute sub-leading terms. And also at criticality, in the critical situation, both critical models, in the one-dimensional critical band matrix or in the two-dimensional fast decaying model, we also detect criticality in another way. We compute the variance of the number of states, which is, in that case, it's pretty small. It's comparable with the expectation as if it were Poisson, but with a small prefactor, which is called compressibility in this model. And this compressibility is it's related to the multifractality exponent, which Fedorov explained to us previously. And what we get is exactly the same thing what is predicted with other methods. So at least there is no controversy here. And we do one more thing which may be of interest. We introduce a generalized hermitian random band matrix where we allow complex variances. So far I talked about the expectation of H absolute value squared. That was the profile function. But in principle, and I didn't really say anything about what the expectation of H squared without absolute value does. But in principle, you can take a model when the expectation of H squared does not vanish, and then this you can introduce a phase factor, you can introduce an additional profile, and then you can, and actually this model you can use as interpolation between the beta equal 1 and beta equal 2 model, and we detect a certain quantity which is responsible, which measures how far you are, how close you are to beta 1, how far you are from beta 2. Okay, so about the proofs, I will not be able to say anything. I just flash up that the new thing here. We use the similar technique, similar diagrammatic expansion what we did in the diffusion paper. It uses first this non-backtracking powers, which goes back to Feldheim and Sodin. This does the self-energy renormalization very effectively. This is one reason why the band matrix is technically much easier, because the self-energy generalization can be done essentially algebraically. Then we do certain subladder resummations with lots of oscillations. The oscillations, the new thing here, we didn't have to do it before. Here we are aiming at a much more precise result, so we have to do that. And actually we have to do it in so precisely that it's an oscillatory sum, and the sum is even smaller than each sum end. So typically you use the oscillatory sum to show that the sum is not bigger than individual sum ends, but here it's even smaller, so I have to do it very precisely. And then one does various power counting. So let me not go through it in details. Those who may have read our previous paper, there were a two-third rule and a counting rule, and that we improve now to the so-called 1/2 rule, which allows us to go to the optimal scale to the -1/2. So here's just the summary. So what we did is that we proved this Archer-Shklovsky formulas rigorously for random band matrices. That's a mesoscopic universality. We found rigorously the weak localization corrections at criticality, and they differ from the physics prediction. So the leading term, the Archer-Shklovsky formula, is correct, that there is no discrepancy, but in the subleading term there is a discrepancy. And similarly, we have a new subleading term in the Wigner case. And this is sort of the moral conclusion for that it seems that the physics predictions based upon these Hikami boxes, whatever Hikami box means, either diagrammatic perturbation or this semi-classical orbit theory, these are incorrect on larger scales, and it seems that the scale is this up to this L to the -1/2 as a threshold. And this is a big mystery, I think, that how comes that it gets, the result is correct, but still it's a completely crazy, mathematically it's a completely crazy regime. And the open question is, of course, one would like to do a similar analysis for the random Schrödinger operator. Everything should hold there, but technically that's much harder. Thanks.